Hello there and welcome to 10-Minute Physics. Our goal today is, in 10 minutes or less, to take a look at Newton's first law, look at some interesting ways to remember and understand, and come up maybe with some tricks that will help you fare better on your exam questions. This could be useful for either Key Stage 4 GCSEs, Key Stage 5 A-levels, or if you're across the pond in North America or elsewhere in the world, whatever relevant education system, whatever exams you're going to be writing. So without further ado, let's talk about Newton's first law now. I no doubt that you probably have some idea. Newton's law is the law of inertia. What does that really mean? And you probably come up with a very wordy definition for it, but I'd like to start things off a little bit differently. I saw a lecture a long time ago by a physicist. I think he had a specialty in roller coaster design, but what the guy said in this lecture was that basically Newton's three laws can all be taken from this simple physics equation, F equals ma. Now, I never learnt it that way. I learnt it as F net equals ma, and I think this is a very key, a very important detail that often gets forgotten. Okay, what does this actually mean about net forces? Well, I'm sure that when you were in middle school or in Key Stage 3, you talked about having competing forces, and so there'll be, let's say, a force 2 acting in one direction and a force 1 acting in an opposite direction. So if you've got F2 minus F1, that is your net force. That is your resultant force. Now, this could mean several things. If you've got an aircraft, it could be lift minus the weight. If you've got some sort of thing floating upwards, the buoyancy, we've got upthrust minus weight. I know it's a little more complicated for cars and vehicles, but if you wanted to take a look at the thrust of a jet engine minus the drag, there would be the horizontal. You've got the vertical component for the lift weight, and you've got the thrust and drag as being the horizontal component for the plane motion. But you get the idea that in any direction we have a net force, and there needs to be some sort of tug of war, if you will. Which of these forces is larger, and therefore in which direction will, because these are vector quantities, in which direction will this object move? And so whatever the net force is, that will give you an idea of what the acceleration will be based on the mass that you have. Or you could work it backwards, but that's more for Newton's second law. We'll talk about that later, okay? But I think a lot of people tend to be taught this version of Newton's first law. An object will remain in its state of motion unless acted upon by an external unbalanced force. Well, what is that external unbalanced force? It's this net force. F net equals ma. And I always tell my students to make sure you write that in there. It's an F with a little subnet to remind you that you're actually saying, hey, I've got a force going in one direction minus a force going in another direction. And it's the resultant, it's the winner of those two forces in their little tug of war, which will determine the direction of the acceleration. I hope that's helpful, because I feel like if you neglect this F net, what students will do, I'll write my student errors in red. They'll just say F equals ma. They might forget to subtract. You might have some other things going on, and they will look at this force here as being just one measurement, one value or something, okay? Don't forget that forces are vectors. You need to add your vectors tip to tail. You need to find out what is the correct direction once the net force has been determined, okay? Now, if you can understand that, you can apply it to our definition of an object remaining in its state of motion unless acted upon by the external unbalanced force. It's quite simple here. If you have no external unbalanced force, that means that whatever two forces are competing are actually equal. An object that is already moving, if there is no net force acting on it because these forces happen to be equal, then what does this mean? If the F net is equal to 0, it means this acceleration has to be 0. And if there's no acceleration, this object will not be speeding up or slowing down. This is what's happening with terminal velocity, where you have here your drag being equal and opposite to the weight of the skydiver or whatever object is falling at terminal velocity. Okay, and it could be maybe you are moving along and an object is moving in a certain direction and it has a velocity. I'll draw this as a velocity vector so we don't forget that it's, don't get confused with it being a force vector. If you've got an object moving along at a certain velocity and there is no forces acting on it, such as an object thrown in space, then no net force means no acceleration. No acceleration means no change in velocity. Remember that acceleration is our rate of change of velocity. If the rate of change is 0, it's because the acceleration is 0. If the acceleration is 0, it's because these forces are equal to each other, and the net force is 0. So hopefully this kind of ties it all together for you. I guess there's one other example we could talk about external unbalanced forces, and that might be if you take a look at the two-dimensional, right? If you were to take a look at the two-dimensional nature of an object being thrown in an arc, okay, what could you say about that? Right? So you've got an object that's been thrown, it usually arcs up and then falls back to the ground or it's caught or something. Okay? But what's happening there is we can often assume horizontally speaking, F net is equal to 0. But vertically speaking, F net is not 0. There will be some sort of external unbalanced force. What is that external unbalanced force? The net force in that case is the object's weight, mg. Okay? And of course this causes an acceleration due to gravity. You know that g is 9.8 meters per second squared. And so that is going to cause this vertical component, which was originally going upwards, to by the end of the journey for it to be going downwards. And that is because it's an unbalanced force acting towards the center of the other Earth. In our point of view, it's acting downwards. More specifically, in circular motion, you will have an object which is rotating about a center, and as it's traveling around, the magnitude of the velocity stays the same. It's the direction that changes when you have circular motion. It's the centripetal force which is the net unbalanced force. That's how circular motion works. And so this is how you can have an acceleration which is, in this case, not necessarily a speeding up or a slowing down, but a changing of direction, because an acceleration can cause a change in direction as well. Why? Well, because you know that velocities are vectors, and if you change not just the magnitude, you can change the direction. If you've changed the direction, you've changed the velocity. And if you've changed that velocity in a certain amount of time, that's an acceleration. Okay, so I hope that we've linked for you here. I hope this makes sense. This external unbalanced force, what does that mean? That's this F net stuff here. And so that equation that you probably have been told to associate, F net equals ma, you've been told to associate that with Newton's second law. It actually is very vital to kind of understanding Newton's first law. Okay, so if an object is at rest, it will stay at rest because acceleration will be 0. If an object is moving along at a certain velocity, magnitude and direction, it will maintain that magnitude and direction, right? And that's what we mean by state of motion. State of motion is either at rest or a constant velocity. Okay, and either one of those is a state of motion, and that will remain unchanged unless your net force is not equal to 0, and therefore your acceleration is not equal to 0. Okay, so I hope that's made sense for you. Please keep that in mind. I think the key takeaway here is F net, and always think of that as being a difference between a minimum of two different forces in two different directions. Thank you very much, and we'll see you next time.